Welcome everybody to our first podcast. Today we are gonna have a conversation with Tim van Schagen. I could give an introduction, but maybe it's more fun if he gives it himself. So please introduce yourself.
Yeah, sure. Well, as you already said, Friso, my name is Tim, and I'm currently working as a PhD student here at the University of Twente within the Sustainable Process Technology group. And I'm working on developing a novel reactor concept for making methanol sustainably with CO2 and hydrogen. And also before that, I did my bachelor and master studies also here at the University of Twente, and I was also involved with Alembic. So yeah, that's a very short bit about myself.
Okay, amazing. Those are also a few of the points I want to talk with you about. So I wanted to talk about why you came here to study and what you did besides studying, and also mainly about your PhD, like what you do within the research group.
Yeah, sure.
Thanks about that. Okay, so first question is, why did you came here to study?
Well, it may not have been immediately obvious since I'm actually from the west of the Netherlands, from the region near Alkmaar. So Enschede is quite a long way from there. But yeah, when I decided I wanted to do chemical engineering, I also looked around different universities, Delft University, also Eindhoven University and Twente. Went to visit open days and also student for a day activities. And I found that the atmosphere here at the University of Twente was really nice. A really friendly atmosphere, low level connections between people. So I kind of felt at home also here when I was walking around the campus. I also enjoyed the campus, of course, everything at the same location. It's kind of studying in the Center Parks environment. And since I liked it here so much, I decided to go here. And also immediately had to move to Enschede, of course. And during when I was a student, I lived at the campus, also in a student house. So yeah, that's very briefly why I chose to came here to Enschede.
Okay, it's very funny because I can really relate to that because for me it's all very similar. Like I'm from near Utrecht.
Yeah.
But also like I looked at different universities and eventually I chose this university because of the atmosphere. Like on my student for a day, after the break, like there wasn't a practical, so my like the one I was working with, he dropped me off at Alembic, and I stayed there the entire afternoon playing potters.
Yeah. Nice.
So yeah, I like that the atmosphere and everything is still the same.
Yeah.
That's
yeah.
brilliant.
Yeah, and I think that's one of the key characteristics, maybe of the whole university, but especially of the chemical engineering department here.
Yeah. So that's why you came here to study, but like you did your bachelor here.
Yeah.
I think you did everything besides the board year. Like you did every module. Like you got all ECTS, right?
Yeah.
You're also the first year that Tom started. What
Exactly,
you told me
yeah.
before. So how was that actually? Because when you did a student for day, it was a different way of studying. Was it also already being applied a bit? Or?
Yeah, well, that's a good question, of course. I think that when you do the student for a day, you did not notice the difference so much. The lectures are kind of similar still. I think the implication of the Twente educational model is especially in the way of examining and the integration of the projects, but you do not really experience that as a student for a day. But yeah, as the first year of the TEM system, we were kind of the guinea pigs to test everything. But I think it worked quite well. Also, there were some let's say initial issues that were encountered, but I think also the education staff, they really worked with us to solve these things and to make it the best experience possible. So I think for myself, I did not experience any negative aspects for this, but I can imagine that this, let's say, stricter guidelines of all the credits per module, if you pass everything, but none if you pass not and one thing not, then that can have implications for other people. But I did not experience this myself, so it's difficult to say. Yeah.
Okay. So another question I have is, you were very active at Alembic. You also did a board year here, but did you become active immediately in your first year? And what did you do?
Well, yes. In my first year, I think I already joined the ICT committee, the ASO. I think it's still called that way.
Yes, it is.
So yeah, that was, let's say, my initial involvement in Alembic, and later I also joined several other committees. I did the Kickstart, so the introduction period, organizing that for the chemical engineering students. I also did later on the training committee. I was involved in the CAT at some point, and I was involved in organizing the study tour to Japan for our year. So yeah, a lot of things. But yeah, I really like the atmosphere at the association, and also the fact that it's really active. We try to organize a lot of stuff, also, and we try to involve also all the other students, and that's why I also felt it was very nice to do this board here. And I thought also, yeah, at this point, at the beginning, it was especially I just kind of liked doing this, but later on, I also realized that I actually learned a lot from it. So yeah, it was just nice to be able to do something back for the association, I guess.
Yeah, yeah. I can quite relate to that as well as a board member currently.
Yeah.
But like, what convinced you, especially to do a board chair? Like, were there certain points you wanted to learn? At your certain goals set for yourself, or?
Well, I think when you start with this is not so immediately clear. I think this will also, let's say, develop when you start and during this board year. But I also like, of course, a lot of my friends and yeah, the people from my year also wanted to do this. So yeah, working together with them to do this and organizing all these activities for the association was nice. And I guess also one of the points was that at that point I was already really involved with all the ICT things at the association, and there were a lot of things going wrong at that point. So doing this board here and also being the internal affairs person was also a way to help the association in that regard. So I guess that's also part of the reason why I wanted to do this.
Okay, I think it's very funny that you mentioned this because the ASO, like especially our board currently, is still thinking of the best people within the ASO over the years. On top are you and Lars van Veldschoten.
Yeah.
So I still think that you're like some kind of hero within the ASO.
Yeah. Well, yeah, it has been some time that I did something for the ICT, but it's nice to see you still look back on this period, I guess.
Yeah. Yeah. So what did you do for the ASO, especially because you told me before this podcast that you were quite passionate back then, especially about ICT. So
Yeah, well, actually, just before I started as a board member, we had a large crash of all the ICT systems and the servers and the mail and everything, and it was due to power loss at some point. But that really messed things up because our entire infrastructure of the ICT was gone, and we had to build this up again from the ground. So I was really involved in this in the beginning, and later on we also really realized that it was very important also to document everything very well, so that in the event of something unforeseen happening, there's already a lot of documentation that people who are maybe less experienced can refer back to. And this is also a large part of what I did on this particular topic during my board year. And beside that, I worked on several projects. For example, I think the member administration system we worked on during my board year, and some things for the website and the touchscreen and these kind of things. So yeah, in that way, I try to keep myself busy with that. But I did, of course, a lot more things besides the ICT.
yeah, of course, yeah.
So yeah, maybe one of the things I also worked upon as a internal affairs person was, of course, the working together with all the committees of the association. We, of course, have a lot of committees. Well, at that point we had, maybe we still, I don't know how the situation is now, but I guess there's still a lot of committees.
Yeah, 23 out of the top of my
Yeah,
yeah.
Nice, very nice. So keeping everything in check and make sure that all the committees run smoothly is also, of course, a very important task because, yeah, we have a lot of members who are active for the association, and it's nice that they, that they can really contribute everything. So it's important to work together good with the committees, and also that you learn from each other. And also one of the things we worked on in the during my board year, what I was also involved in, is the let's say reorganization of the study tours. Because before our year, it was usually a small committee of 5 people who organized the study tour. But because of the new education system, especially, this was not feasible anymore, because there were no people willing to organize this with a group of 5, because it's a lot of work. And then we designed a new system where we did tasks of organizing the study tour would be distributed among all the participants. And this also, we had to set this up during our board year. And actually, I was also the participant of this first study tour in the new system. So there was kind of a nice crown on the work, let's say.
Nice. Was that like especially the committees? Was that also why you specifically solicited for the function of internal affairs, or were there other functions you wanted to do at first, maybe more than this function?
Well, I had 2 preferences: either internal affairs, based on the reasons I described, and also treasurer. I would was one of the options, because also I liked working with money and numbers and these kind of things. But I guess in the end, I'm glad that I became the internal affairs person, because I felt that I could contribute a lot in this part of the association, and also learned a lot from it.
Okay, great to hear. I wanted to move on a bit from Alembic to other curricular activities you did besides Alembic, because you're also in a dispute. And
fraternity, I think, is the correct word, right?
Fraternity in English? Yeah. I didn't know for sure. I thought dispute wasn't it for sure, but I just didn't know what it actually was. So you are also in a fraternity.
Yeah.
So how did you came to join that?
Well, the fraternity I guess I still a member of is called Silenus, and it consists of former study association board members. We're a male fraternity, of course. The name implies that, I guess. So after my board, or actually during the board year, I was asked for this, and I of course joined them on a few drinks and activities, and I really liked it there, and so I joined them afterwards. And also together with one of my fellow board members, Jasper, he also joined Silenus at the same time. So that was nice, yeah. And within that, of course, we organized all kind of fun activities, especially for ourselves. But it was nice to do it, let's say, besides studying, a nice diversion.
Okay. Were there also other things you did besides the fraternity and Alembic?
I also worked for the university on several occasions. One of the things I was always involved with is organizing the error analysis and MATLAB course for the first year students.
Okay.
I used to give also the lectures with that with some other student assistants. I also supervised some of these self-study hours at some point. I organized trainings, in part with the training committee of Alembic, but also in collaboration with the program staff. I guess these are the main things. Maybe I did some other small jobs, but they're probably less important. Otherwise, I would have remembered.
Brilliant. So all these things were mainly during your bachelor and also your master's.
Mm-hmm.
But then you went on to do a PhD. How did you come to do this PhD?
Good question. I guess we have to go a bit back for that, because during the master program, during the second year of the master program, actually, you have actually 2 parts. So first part is in principle an internship at a company or at a university outside of the Netherlands. And the second part is then your master thesis, which is usually done at the university, although it's also possible to do it at a company. And at the beginning of the second year of my master, I was not really sure if I wanted to go to industry directly after my master, or I wanted to remain at the university a bit longer and pursue a PhD. So actually, I found out that during my internship, which I did at a company, at a production plant, actually, I found out that I really liked also diving in depth into things, which was confirmed again during my master thesis, of course, because that has to be a kind of an in-depth research. And based on that, I felt that I would like it to work on such in-depth research for some time longer. And also what helped is that during a master thesis, I worked on a direct air capture, so the removal of CO2 directly from the air to reduce the CO2 levels. I really like this topic also, which has an environmental impact, a positive environmental impact, hopefully. And I also, had a very nice collaboration with my colleagues at that time, but also the colleagues at the research groups and the professor Wim Brilman. And that's he offered me the PhD position now, which I'm now actually doing research on the methanol synthesis. When he offered this, then I almost immediately accepted because I think it's a very nice research topic, also with in regards of environmental impact.
Yeah. So as you just mentioned, it's about sustainable methanol production.
Yeah.
And you work with Wim Brilman on this.
Yeah.
Like he's your supervisor, if I'm correct.
Yeah.
And you do this via a new kind of reactor, which is the logic reactor concept, which is, if I'm correct, liquid in, gas out.
Exactly.
Concept. That's what it stands for. So could you maybe tell me a bit more about that reactor and how the process works in general?
Yeah, I can. I think I should give the let's say explanation for at the coffee table during a family visit first, and then I can go a bit more in depth. But the idea is that we take CO2. Everybody knows we have to get rid of the CO2 somehow because the levels in the atmosphere are too high. So we take the CO2 either from emissions from chemical plants or directly from the air. And then we have to do something with it, because if we store it, then it only costs us money. But if we can do something useful with it, it may have an economic purpose. And we also have a lot of renewable energy, and we are expecting to increase the amount of renewable energy in the future as well. And we can use this renewable energy, especially when there's an excess of electricity at a sunny day, for example, to make hydrogen sustainably. And this hydrogen we can react with the CO2 to form methanol. And methanol is a very versatile chemical. We can use it as a fuel directly. We can blend it also with gasoline, for example. We can make all kinds of materials from it. We can, based on methanol and its derivatives, is, for example, currently used in the making of plywood and other adhesives. But we can also convert it to the basic building block for all kind of polymers that we are using today. So we can have a lot of options to do with that. And then finally, we can use it as a means of energy storage. You can imagine that in a sunny, windy day, we have a lot of renewable electricity in excess. And if we then use it to make hydrogen and then react it with CO2 to form methanol, and we later on, when we need the energy again, because we do not have enough sustainable energy, we can either burn the methanol or use it in a fuel cell to generate back electricity. In this way, storing it for a longer term, because methanol is a very nice chemical in principle, because it's a liquid at room temperature, and it's also relatively harmless. Of course, there's some safety hazards, but it is less harmful than other components, such as ammonia. And hydrogen also has problems because you have to store it at very high pressure. So I guess that's a bit of the broad context of my research. And a bit more in depth is the problem is that if you make methanol from CO2 and hydrogen, you are limited by the equilibrium conversion of the reactor. So it's an equilibrium reaction, but the conversion you can achieve is about 20% max, which is very low, because you need to recycle all these unconverted reactants. And this is a big drawback and a big problem, and that's actually what we're trying to solve. So what we did is we are integrating the catalyst bed and also a condenser in the same reactor, essentially. And how this works is that we feed the CO2 and hydrogen as a gas. It is sent to the catalyst bed. There it reacts. It also heats up there, of course, because of the reaction heat. And then we send it to the condenser section. In the condenser section, we lower the temperature, and then thereby we condense the methanol and water, which are formed as a product of the reaction. We condense them, remove them from the reactor while keeping the pressure still constant. And then the unconverted gases, they are recycled and mixed with the fresh feed. And in this way, you introduce only gases in the system, and all the products that are formed can be removed as a liquid. Hence also the name, liquid out, gas in concept. And in this way, over the entire reactor, we can get a near 100% yield of the products that we are trying to make.
Okay.
And also by integrating this in a single reactor vessel, we can save a lot of costs because we do not need expensive piping and multiple pressure vessels to do this process. And by having a catalyst section which is hot and a condenser section which is cold, and we place the colder section above the warmer section, we generate a driving force for natural convection, like a hot air balloon. And you know that hot gases tend to rise up, and cold gases tend to go down. So therefore, the hot gases from the catalyst bed, they are moved upwards by the natural convection, and the cold gases from the condenser are moved downwards.
Okay.
So this recycle is also generated for free. This is also what we're trying to achieve in the new reactor concept.
Okay. But then, like, normally it's a way bigger setup, so I can imagine this is way smaller. But at what size, if you wanted to imply this in the future, like, what size would it then be?
That's a good question, and it really depends on the application. Currently, we're developing a setup which can produce about 15 kilograms of methanol per day, which is already quite a lot. To give you an impression, the setup will be about 2 to 2.5 meters high, and also a diameter of, let's say, 20 centimeters or something. But the scale that you want really depends on the application, because if you want to make for example, you capture CO2 from a power plant, and you want to do something with this CO2, then you need a very large scale. You need a very large scale process, and you can probably do this also in the logic concept. But there, I think the advantage of the logic concept would be less pronounced. But for example, if you have a wind turbine or a solar farm, there you have, and you can then directly capture CO2 there from the air and make methanol with it if there's an excess. You do not have to transport the electricity in that case, but you need a much smaller scale setup in the order of maybe 100 to 1,000 kilograms per day. Right. And this is really where the logic reactor, I think, can have its advantages also compared to the traditional process.
Okay. Is the, like your master thesis you did about direct CO2 capture, is that also something you imply currently in this? For example, if you would imply it in a solar farm or wind turbine, is that also applicable? Like, could you combine those two?
In theory, yes. And if everything goes the way we plan, we will try to combine also actually experimentally a direct air capture setup which produces CO2 with a methanol synthesis reactor, because we also have colleagues of mine are working on direct air capture setups which do produce this CO2. So yeah, if we can achieve this in the future, that would be nice, of course, to have an experimental demonstration of this, that it actually works. But in theory, yeah, we can.
Okay. Then with the logic, you mentioned like the most advantageous setup is next to a solar farm. And like everything you told me is quite, like, in my opinion, brilliant. Like, it's very sustainable and everything.
Mm-hmm.
But are there also drawbacks from using this compared to the traditional setup?
Well, that we'll have to find this out. One of the things you could think of is, because we have a highly integrated reactor, we have less degrees of freedom to control the system. So from a control point of perspective, it may be challenging, although this is something we probably also can solve in the future. And for the rest, yeah, I think compared to the traditional process, the main thing is that we just save a lot of costs on the capex, so on the material and the investment costs of this process, because we can do it in a much smaller volume, and we can have a much more integrated concept, which just saves on material costs. So I guess, especially for the smaller to medium scale, we have more or less only advantages I can think of at the moment, except for the maybe larger difficulties with control, and also maybe accumulation of inert components in the system, which you have to purge at some point. Yeah. But these are things you typically also encounter in a traditional process.
Setup,
So yeah.
And from a cost perspective, because there's always our cost implied. For example, what kind of catalyst are you using right now? Is it very expensive, or is it just The same as traditional?
Good question. And we use a traditional catalyst. So it's actually the same catalyst which is already being applied in industry at a very large scale. So the catalyst is relatively cheap. It's for the interested listener, it's a copper zinc oxide on alumina catalyst. And you can just buy it commercially from a multitude of catalyst manufacturers.
Okay.
So
that's nice. And I looked into it a bit before this podcast, but it said on the website where it was mentioned on the people page of the university, it said this logic reactor concept functions at mild temperatures and mild, like in general mild conditions.
yeah.
Like what kind of scale would you consider mild?
Well, the temperatures you could think of is for the catalyst bed, you might think of between 220 and 300 degrees Celsius. So relatively mild. There are processes which are more extreme in that regard. And then in the condenser section, it is between, let's say, 40 and 100 degrees Celsius. So that's also kind of okay. And the pressure is an interesting parameter because it has a large effect on a multitude of things in the logic system. Because lower pressure is in the point of compression, for example, it's cheaper because if you have lower pressure, you have to compress less, so you need a smaller compressor, these kind of things. But the equilibrium is less favorable at lower pressure, and also the reaction kinetics slow down at lower pressure. And furthermore, generating this natural convection flow in the system is more difficult at a lower pressure. So typically we want to go to a higher pressure, but we will in the future also really look into what is now the optimum for this system and what is now the optimal trade-off. Because like I said, higher pressure then improves the equilibrium, improves the rate, and also improves the natural convection. But yeah, you need more costs in front to compress your gases. So this will be a calculation in the future where we look into the sensitivity of all these parameters on the design.
Okay. That was also one I want to ask, like, what's the optimum? But if you don't know yet, then I'm just wondering at what pressures are you working right now?
The reactor we are currently building will be designed for a maximum operating pressure of 100 bar. Okay. And typically methanol synthesis is done between maybe 40 and 80 bar, depending on the specific plant.
Okay, so a bit higher than normal.
Yeah, it is relatively high pressure, but although in industry you can also encounter processes which run between 200 and 300 bar, for example, ammonia synthesis.
Yeah. Like methanol could be used as an energy source, like as a storage, but like getting this pressure and everything also takes a lot of energy. And what kind of efficiency do you then run or deal with?
That's a very difficult question to answer, especially at this point, because you have to realize that if you go for a full sustainable route, there are a lot of contributors to the energy you require. You require energy to get the CO2, either from flue gas streams or from the atmosphere. Typically, what you need there is maybe between 10 and 15 megajoules per kilogram of CO2. Then you need energy to make hydrogen in electrolysis. And all these steps, they have an efficiency factor. For example, electrolysis maybe typically be efficient between, I think, 60 and 80% or something, if I recall correctly.
Yeah.
But then this hydrogen you have is then made with this efficiency, but the methanol synthesis induces another efficiency step because the methanol has, in principle, less energy content than the hydrogen because you release some energy during the reaction. So all these conversion steps you do, they incur an efficiency penalty, and that makes it very difficult to estimate what the overall efficiency of the process is. It depends a bit on what you consider.
Yeah.
I think in general it is storing electricity in the form of chemicals incurs an efficiency penalty, which can be quite high. I think the efficiency may be between 30 and 50% or something like that.
Which is already way higher than it normally is.
Yeah, but for example, batteries can have a much higher efficiency. Yeah,
that's true.
So you incur an efficiency penalty, but I think the most important aspect of this is that in the future, when we have a very sunny, windy day, we have a lot of excess of electricity. So we can permit ourselves to lose some efficiency and store energy for the longer term. Because that's really the advantage, storing energy for the longer term. And because batteries, if you would construct batteries on the megawatt hour scale, for example, it becomes very expensive very rapidly. While storing energy in chemicals, can be done relatively cheaply. So it's kind of a trade-off between these two things, I think.
Okay. And is this the first time that actually somebody is researching the logic system?
No, I had one, let's say, predecessor who worked on this concept before, Martin Bos, also together with Wim Broman, of course. And what he did is, they conceived the concept and they proved experimentally that it worked on a very small scale setup. And now my main task is actually scaling this up and also investigating whether we can use this natural convection, whether we can use sufficient heat integration also in the system, and whether we can really identify the key optimal parameters to run the process on.
Okay. And you're currently in the second year, if I...
I started in November 2019. So I'm now almost 2 years underway.
Okay. Nice.
Yeah.
We'll look to my assistant real quick and to see what time we are. Which looks okay. I don't have any questions furthermore. Is there anything else you want to talk about?
Well, maybe I can talk a bit about, in general, a bit about doing a PhD also.
That would be brilliant.
Yeah?
Yes,
if
please.
you would like this.
Yeah, I like it a lot.
Because obviously you have to do research. Because you have a project, you have to do research, and you have different kind of projects. I think in general, in my case, I work together with some companies on this. So there's also a bit of, let's say, a commercial aspect to this. You also have more fundamental projects which are funded by government agencies, for example. My project is really applied, and that I like that because I like it. I like to see what's the implications of what I'm working on directly. Yeah, that is nice. And then beside the research work you have to do some courses, apart from the university, and also some more content-wise courses from other universities or organizations. And these courses range from different topics. For example, giving presentations in a presentation academic context, how to supervise students, because that's also one of the things you have to do. How to publish your work, these kind of things you can think of, but also more content-wise courses, which depends on your project, of course, which your courses are relevant. And then I mentioned it already briefly, you have to supervise students, and this works in two ways. You have to supervise bachelor and master students, and personally I really like this because this also really contributes to your own project. You kind of work together with someone to investigate a particular part of your project. And examples of project students of my who I supervise now work on are the kinetics of methanol synthesis, so investigating the rate of the reactions and making a model for this. And also investigating how this natural convection behavior affects the heat transfer and also the flow in the system. And there are a multitude of other topics as well. I personally enjoyed it to work together with such students to investigate these topics, and I hope the students also enjoy it. But they should answer that. And then the second part of the supervising is also you have to participate in organizing some of the courses that you as a student also have to follow. You have to supervise some practicals, you have to supervise some projects, and you also have to supervise tutorials, for example, in some cases. And it's part of the job. I also like doing this, but it depends a bit on the person. Yeah, it's just it's kind of it's part of the deal. You have to see it like this.
Yeah, and is that like the supervising part, which you normally wouldn't get in a company? Is that mainly what made you choose this? Because you already said you like the applied part, but if you were to go on and work at a company, you would also have that, right?
Yes, that's true. But I think it depends a bit on in what company environment you arrive. If you arrive at an R&D department, you also have this in-depth research. But usually, when you want to work in an R&D department, a PhD is either really preferred or a prerequisite. So then you have to have this. And if you work as an engineer in a plant, for example, you have much less time to do this in-depth investigation. Then you have to solve the problems or optimize the plant on the longer term, which is quite different. So supervising, I think it's not really the reason why I chose it. I think it's especially doing research and also in a relevant topic. That's nice. And I think also very important in deciding whether you want to do a PhD, yes or no, is the particular topic. And you have to question yourself: do I see myself work on this topic for 4 years? Because it's really your own responsibility, and you really have to organize it by yourself. You have to make a planning and these kind of things. You have to do this by yourself in principle. It's your own responsibility.
Yeah, of course. Like, you really have an interesting topic, at least I would say. Like, the sustainability is something that is a major topic, especially recently. You heard a lot about it on news. So if you were done with this, would you want to go on and work at a company that implies also this, like, for example, the logic system, or would you go on and choose something else? Might not be something you've thought about a lot. I could understand.
It's an interesting question, and I guess it depends partly on what the result of the research will be. If the concept really works as good as we now envisage, then maybe we have to apply this in the industry somehow, and then that there may be also a role for me in this. But I don't know at this point. I do know that after finishing my PhD, I would like to work in a company, maybe at an R&D department or somewhere else. But I also like to have this experience within a corporate life.
Yeah.
Later on.
Okay. Nice. I think that's basically the time we have.
All right.
If there's anything else you want to mention.
No, I think that's it.
Okay.
Well, let me then thank you also for the opportunity of telling something about my research and also my experiences here at the university.
Yeah, and if I'm correct, you told me that there was a podcast posted yesterday about the Dutch process technologies, the MPT.
Yeah, exactly.
I think that's in Dutch, though.
It is in English also.
It's also in English.
Yeah.
I think you were to go more in depth in that one, or about this topic also.
Yeah, and it's also a bit more about sustainability in general and the role of methanol in this. And also a bit of my personal experience, but less focused also on my time at the university as a student.
Yeah. So for anybody that wants to learn more about this or hear more about this, please check it out. It's on Spotify.
Yeah.
If you search for MPT podcast, you will find it.
Exactly.
Besides that, I really want to thank you for your time and for being our first guest.
Yeah, no problem.
And
glad to be here.
Yeah, thank you very much. And that's it, I think.
All right.
Have a nice day.
Thanks.
Okay.
You too.
Bye.